I guess we can say it Starks over EC paper, or Starks using elliptic curves. So there's quite a lot going on in this paper. I guess if you could, yeah, maybe just start like give us an overview of the sort of main adaptations you had to make. And really, what are the sort of main results of the paper? So I guess we could say, oh, sorry, go ahead.
Dan, would you like to start?
Hi. Yeah, so this is about the VC50 part 2, right? Mostly. Yeah. So the main motivating reason for inventing this CCF50 version was in order to enable Stark proofs to work over finite fields which don't have these FFT-friendly multiplicative groups, cyclic groups. Actually, I think David can probably tell you a bit more about the motivation, because he is the one who invented it. But as I understand, it was mostly about originally about binary fields, actually, that you have the additive FFT, but that one doesn't have a cyclic nature. It has a group with large rank in it. And that's helpful for Starks, where really this cyclic group is what you want in order to make the arithmetization very efficient. So that was, and as a side benefit, it also works for any large finite field, for prime fields also, and not just for binary fields. And then this new FFT basically enables doing the same kind of arithmetization that was used for classical Starks, and doing it over general fields by arithmetizing the computation in tables that are evaluations over this special set of points, and as functions over the curve instead of just the roots of unity. You have the structure that you can shift by a point, and you get other functions defined over the curve with the same properties, and then you can multiply this function and you get functions with nice properties too, and everything just magically works.
I have a question. So, okay, we have, if we just quickly sum up sort of the main differences from normal FFT or normal Phi, you have this big, coset, which you can just fold with the squaring map. And here, instead of doing that, we have this sequence of elliptic curves, which have some subgroups, and then we have a sequence of two isogenies connecting them. In the proof, and then you can project that onto, P1. So in the proof, there's an existence proof for this with the commutative diagram and stuff, but I assume in practice for this version of Phi, we need to actually know what those maps are. I think they're called psi. Do we have a way of, I couldn't find where it said anything about that.
Well, I think we do give the concrete construction in the paper, right then?
We give the heuristic algorithm that you developed, and we give an example for a binary field, a specific polynomial that we found for specific
yeah,
curve.
the heuristic algorithm you're talking about, finding the curve, right? The first curve. But once you have the first curve,
yeah, but I also mean finding the size.
Yes, once you have the first curve, finding all the psi's is a very simple method which I think we do we do show the method in within the paper.
Yes, this is in section 4.1. It's just basically from the coefficients of the curve, where you have this formula of EAB square, where the curve equation is y squared equals x cubed plus ax squared plus b squared x, which is slightly different than the usual Varcho's form. But it works for any characteristic which is not 2, including 3. Then given these a and b, you just get a very concrete formula for what phi is in terms of a and b. And same for the psi function, just very pretty short formula.
Okay. I'll look at that. I just didn't see it, I guess. I guess as a follow-up to it, I mean, working with isogenates and elliptic curves in general is going to add a lot of overhead, but is the plan here that you just pre-compute all of the relevant things and then you can pretend that you're just working over subsets of the finite field?
Yes, it's not. Yes, you generate all this, all the heavy elliptic curve operations are actually in the pre-computation, and then the FFT itself only uses these values as Twiddle factors. The only thing that actually happens within the protocol itself after the pre-computation that actually involves the elliptic curves is the evaluation of the domains, the how it's called, vanishing polynomials. You need to evaluate vanishing polynomials of the domains. This happens, the verifier and the prover do it without pre-computation.
Right, and that's one of these elements of the Riemann-Roch space on this invariant thing.
Yes.
Like a rational function on the curve.
Right.
Yeah.
I want to introduce also Eli, which joined us. He is also a co-author. Can you?
Yeah, hi. I was muted. I'm just listening in. But you're talking to the real experts. I'm just listening in and enjoying. Hi, everyone.
Can we go back, David, to your motivation then?
Okay, the main motivation actually was that you cannot do FFTs in fields that are non-friendly. The reason is that the multiplicative group, which is the group in which you do FFT, usually is not smooth. It is not divisible by small primes, no, by enough small primes. This is for a general field, right? And sometimes we are actually restricted to work in a specific field which might not be FFT friendly. But there is an example where there is a field with a multiplicative group which is not nice, but there is an FFT in that field. This is called the binary field, and the reason is that the version of FFTs for binary fields is it works with the additive group instead, which is of very smooth size. So this gave the motivation of looking for a different group that would be both smooth and defined over any field. Such groups exist, and they are called the elliptic curves. And actually, this is not the first time in history that this state of mind happens. Actually, this is very analogous to what was done in the ECM algorithm. It's the elliptic curve method of factoring numbers. There was a method that is called the P-1 method that given a number that is divisible by some p, such that P-1 is very smooth, you could factor that number. So the ECM method takes the same this P-1 method and extends it to this elliptic curves groups, and instead of doing it only for specific numbers, it does it for any number. So in an analogous way, we also do an FFT that works for any field.
How do you estimate, what do you estimate the, extra overhead to be? I don't know if you implemented it yet, but I haven't seen anything. By using elliptic curves, is it something like working over the quadratic extension? What would you?
The FFT itself doesn't have any overhead because all the extra operations happen only in the pre-computation, which is linear in n, and the FFT is n log n. So all the extra operations happen only in the of n in the beginning, and the Stark, actually, it does have a bit of overhead, which is in the, as I said before, at the computation of the vanishing polynomials of the domains. And there, I'm not sure how much overhead it is, but it's a small constant. Only for that part.
Okay, so you do see this being, in its current form, practical, if not as efficient as, when you have very phi-friendly fields, it would be able to compete with, many proof systems that are currently considered state of the art.
Yes, it is very competitive to the state of the art.
That's very cool. Very cool. And you've implemented it or not yet?
Not yet.
Okay, we implemented some of it.
Okay. So mainly we're talking about asymptotics, and the constants are still not, we're still not completely sure about the concrete efficiency, or how is that?
Well, we did look at each part individually, and I actually did implement the low degree extension version of the FFT. So this is actually this part, the FFT itself, was actually you have this pre-computation, which is of n, and there is some constant in this of n, but it's not n log n, and this constant is, I don't know, a small number, higher than 1, but still small number. And then the n log n part, which is the main part of the FFT, it's actually the same code, exactly the same code, exactly the same loop. I didn't change anything.
So the main advantage of this is you can use it. I think the example used is like the field of fractions of Bitcoin curve or something like that. The main draw to it is for those specific cases where you actually need to use. There's some crypto system that depends on particular fields.
Yes.
You would use that. That's kind of the one motivating factor.
Right.
Yeah.
Yeah, and I think another use was the for binary fields where you have addition being bitwise XOR. So that could be nice if you have to implement things like classical hashes, which are not finite field based.
So does it make sense to incorporate this? Off the top of my head, I'm not sure exactly how it would work, but say for something like, I mean, Starkware has these like universal computation, and if you want to do non-native field things, it's a bit annoying now. But on the other hand, can you make these different Starks over different fields play well together?
You mean to generate proofs that involve different primes?
Yeah, and which can be verified over the respective fields without too much overhead or the different fields.
Eli, would you like to answer that?
Sorry, could you repeat the question? It was spaced out.
Yeah, so you have these different variations of Fry or say of Starks, which work over different fields and can serve different purposes within, say, a greater ecosystem, say something like StarkNet, where you want to validate signatures and stuff. So you think it's viable to verify, say, elliptic curve Fry signatures in normal, Goldilocks, normal standard Fry?
Sorry, you broke off. If it's
yeah, just about if the proofs in one of these proof systems is easy to verify without too much overhead in, say, standard Fry.
okay, I understand. Like basically arguing about one prime field within, or with one finite field within another finite field, right? That sort of
Yeah,
question.
exactly. Yeah.
Okay. So I mean, that's a terrific question. There are a number of different ways you could do this. Let's count, let's say at least 2 or 3 of them. So one is to argue somehow outside the system. So for instance, that's maybe the easiest. So suppose we have, well, let's just focus on 2 different moduli. You have like modulo P and modulo Q. So you could just, let's say you have 2 smart contracts. If it's on a blockchain, or just accept that things are proven both mod P and mod Q, you can accept that. So that's one solution. So just to make it concrete, today, we implement Cairo and Starknet using one very specific modulus, but maybe tomorrow there'll be, the verifier smart contract at layer 1 Ethereum will say we can accept also, things mod Q. Okay, but that's an easy trick. Another one that is already implemented today, for instance, over Cairo, is it's also like a kind of trivial, but it's actually pretty efficient, is to simulate one field within the next, within the other. So for instance, right now, inside Starknet in Cairo, we have this built-in that allows you to do bitwise operation on, I think, 16 bits at a time, and it's not too costly. And you can, within log q many bits, you can simulate log modulo q operations over FP, right? And often it's not too bad, because if you think about verifying, let's say, one start within the other, like 90% of the verification is about commitment schemes. And then suppose you want to do something, you have a proof modulo Q and you want to prove it modulo P. So 90% of what you need to prove is about hash functions and opening Merkle trees. And if you know you're going to work in modulo P, so you could use just use, let's say, Poseidon over modulo P, even when you're hashing with elements from FQ. And then you have the remaining, let's say, 10% that is like linear algebra or just mod Q operations. And yeah, and then they'll be more costly when you use something like the built-ins for bitwise operations or for integers, right? And the last thing, which is the coolest, and I mean, we have some preliminary thoughts on this, but we need to write them up and check them, is like to do a more algebraic kind of way to argue about things mod P in a world mod Q and vice versa. And well, once we have that written up and we checked it and everything, we'll be happy to come on again and elaborate on how that could work. But let's put it this way, the three of us were optimistic that there are ways to also do a little bit better, at least asymptotically, and argue directly FP over FQ and vice versa.
You were kind of hinting to maybe you could, well, I'm not sure how that would work soundness wise, but that the polynomial IOP works over FQ, but the polynomial commitment scheme is over FP.
Sorry?
So these proofs consist, like you kind of have the modular parts of the polynomial IOP on the one hand and the commitment scheme on the other. And you said that 90% of the stuff that's done is related to the hashing and the commitment scheme. And if you do that over the base field, that's good. Is it possible to have a polynomial IOP which is not tied to the same field as the commitment scheme?
No, not really, but it doesn't mean you can't do things even if it is. Like, yeah, the field FP and the field FQ are completely different, right? So you can't really, even any field element that is other than 0 and 1, probably just, they behave very differently mod P and mod Q. So yeah, you can't really, polynomial commitment over one field doesn't necessarily make sense over the other field. But again, I like, you can still do some tricks and games even there. But I prefer not going into details before we checked everything and wrote it up and made sure that it makes sense.
Yeah, sure. Thanks.
Yeah.
Oh, we've got a question in the chat from Ulrich. He says, as I don't know anything about algebraic geometry codes, rather fundamental question. So first, are Gopher codes better error correctable than Reed-Solomon? For given error bound, are the list sizes smaller?
Yeah, so I don't know much about algebraic geometry codes in general either, but the specific codes that we have in the paper are actually really equivalent to Reed-Solomon codes in the end. And just there are two kinds of codes that we consider. One is for rational functions evaluated at the at FQ points, and those are just like polynomials divided by a constant function, constant specific function. So they are just equivalent by multiplying by this constant function evaluated at the points of evaluation, which are just constants at every point. And this means that the distance is exactly the same, because they either agree at the point or disagree to point the same as whether the polynomial in the numerator agrees with a polynomial or not. So they have exactly the same properties for decodability and error correction and so on. And the second kind are those that are evaluated at the points of the curve, and they are rational functions with certain denominator for the curve, but those two split into two rational functions evaluated at x. One is multiplied by this zeta thing. So again, these codes are just really equivalent by, in this case, a 2-to-2 linear transformation, which is similar to the Frey step that we have there, two linear codes with exactly the same decodability properties. So they have exactly the same properties as far as proximity gaps are concerned. So that's nice. You really don't have to know a lot about algebraic geometry codes in general in order to understand why Frey works for those codes.
I want to add something. So for general algebraic geometry codes, so I mean, algebraic geometry codes received a lot of fame in the 70s and 80s because of some very spectacular results in classical error correcting code. There was a famous paper by Vladut Tzfasman. It's hard to pronounce the name. Tzfasman Vladu Zink, who showed that a very, very complicated and very high genus algebraic geometry code over constant size fields gives certain error correcting code parameters that are even better than what random linear codes achieve. And this is like a very famous result. So general algebraic geometry codes of relatively high genus, and they're like very complicated. I don't claim I understand them. I think that, for instance, even having polynomial time algorithms for writing down a basis for the linear code and things like evaluation and certainly decoding them as error correcting codes, I think in many cases they're not known. These are like open questions. But one way to think of them, or at least that I think of them, is, well, they're like polynomials, but the main advantage, so they're like polynomials in many important things. You can associate some notion of degree to them, and roughly they are sort of what's called MDS, or maximum distance separable, which could be explained as the distance plus the rate roughly equals 1. But there's, okay, so like in that sense, they're a little bit like Reed-Solomon codes. But now here are the important differences. One is, and this is the advantage, they have very small alphabet size. They could work over, you could get arbitrarily large block length over constant size fields, finite fields, okay, which you can't get with univariate polynomials. You need the field size, the evaluation domain, to be larger. And with AG codes, you can work over, let's say, I think the smallest effective field for which they get very impressive results is 49. So you could take the field that is of size 49, and you could get arbitrary block length codes that are a little bit like, you know, Reed-Solomon codes. So that's the advantage. And they have some notion of degree, and they have what's called the multiplication property. So when you take two different code words and you pointwise multiply their entries, you get something of roughly twice the degree. On the downside, there enters this messiness. They don't behave like polynomials, and the amount of how much they misbehave is somehow related to their genus. So the higher the genus, the more messiness comes in, the more they're not MDS, the more there are certain tuples that are not, how do you say, linearly independent and all sorts of stuff. So they're a bit like polynomials, and they're even a bit like polynomials in all the things you would need to do something like a Stark or a PCP or these constructions. You could imagine some sort of snark over them, maybe. or a fry, but they have this added messiness to them. By the way, there's a lot of terrific questions about like general AG codes. For instance, can someone do something that's like fry for like general, like, you know, one of these fancy algebraic geometry codes, like the Vladu, Fassman, Zink parameters, or Garcia and Stichtenoth have also a construction of algebraic geometry codes. So can someone get a version of fry for those codes? That would be nice.
I think there is a reason to work on that. I think there was a PhD thesis by Sarah Bourdage. I don't know if you're familiar with it. I can send it in the chat.
Yeah, I know. There's a very nice paper, but I don't think David and Dan, you remember that paper, right? The one by Sarah Bourdage and Daniel Ogu, and I think Jade Nardi.
I remember, yeah.
Yes,
don't have
I was muted. I think I do too.
So it does, okay, it for sure does not resolve like this question of general purpose algebraic geometry codes and how do you, even if they're built on towers and like those fancy things. I think they had a conditional result, which like if the curve or the AG code has a certain structure, then some nice things happen. But I think it was not known which codes have the needed nice property, and I think it may have been even a bit worse that no such codes could exist.
Okay, I'll send the thing in the chat for the people who are interested, but that sounds reasonable.
And I see Ulrich also had a part 2 to his question. He asked about, is there any hope for proximity gap theorem with larger distances or tighter bounds, and any research going on about that? So I think we can say that we are still thinking about that. We don't really have any concrete direction right now for that, but that would certainly be nice to have.
Yeah, I can add to that like two concrete special cases that would still be very interesting. One is, can you prove that if the initial function is, let's say, a very simple rational function, let's say 1 over x, can you prove that, you know, the worst attack on 1 over x as your start function, if someone uses fry, is basically the conjectured bound, like, you know, the rejection probability, no matter what the prover does, would be 1 minus rho, where rho is the rate. That's one interesting case to consider. And the other interesting case to consider is the case of a function that is random. So, you know, think of an attack where the initial function that is committed to is just purely random. So it's, you know, very far and has no structure. Can you show that now there's no effective way to continue the protocol that will give you rejection probability smaller than 1 minus the rate? I think even just understanding these two cases would be extremely interesting. The rational function probably even more interesting, because right, is the question understood? So like, what happens if the very first function that is committed to is the function 1 over x? So we know that 1 over x is very, very far from polynomials of degree d. That's an easy exercise to show. So now the question is, can you show, well, either way, like, can you show that there's some strategy for this particular function that would, with high probability, lead to surviving a single query phase of fry with probability, let's say 2 times O for a very large field? Or else can you prove that with high probability over the verify randomness, and no matter what prover strategy, when you get to the query phase, the rejection probability with high probability will be less than, I don't know, 1.1. Sorry, the acceptance probability will be less than 1.1 times O.
Ulrich's also asking, so what is known about the performance encoding these specific Gothic codes versus Reed-Solomon?
Sorry,
Yeah,
what is known?
About the performance encoding these specific codes?
Performance in which parameter?
I think it's about the performance of the encoding itself, is how I understand the question. Which is the encoding is basically just doing this LDE using the ECFFT that we developed in the 2 papers. And as David said, it's basically exactly the same as an LDE using regular FFT, exactly the same computation cost. So it's exactly the same as encoding of Reed-Solomon codes with where the evaluations are cost sets of powers of 2 multiplicative groups. Welcome.
Great. Do we have any more questions? Anyone wants to jump in? Looks like not. I'll just ask. So, are the next steps a full implementation then? You said you've implemented parts. I guess the finding the curves, that algorithm must be implemented, right?
Well, I actually, yeah, Ali.
Yeah, go ahead.
I actually implemented finding the algorithm in a very brute force way. So I didn't find a very good algorithm, a very good curve. For binary fields, I did find a nice curve. And it was mainly research code. It's not production or something like that. So
I'll elaborate a bit. Right, Starkware has all kinds of like very concrete objectives in terms of what needs to be done. So basically Stark technology is adopted. Now ECFFT is among those things that greatly improves performance for very specific use cases, right? If you want to do Bitcoin signatures. Right now, the main thing that is blocking us and that we're focusing on is in other areas. For instance, a lot of effort is on getting StarkNet and Cairo 1.0 and performance of the sequencer, not even in the prover. And all of that is focused just on this very, on the original, somewhat clunky and certainly very large prime field that everything is built on. It's very convenient. It's a very large field if you're using a Stark. It's around 252-bit prime. So it's somewhat clunky. I think that, okay, and we'll stick it with it for quite a while. I'd say at least for the next 6, probably 12 months, maybe even longer. We'll not put anything in production, I think, that isn't over this field. By the way, I should mention that over this field, there are already a number of libraries that actually do simulate other moduli. Quite a large number of them. So, right, the simple approach of just dealing, brute force with other moduli is already something that is happening on StarkNet. So it's much less efficient, of course, than ECFFT, but or ECStark, but it doesn't require any changing of Cairo or the basic proving system. If I have to guess what might come next at some point in the future, it would be maybe adding a smaller
I think we lost you, Eli.
At the worst time possible. Huh?
I think it was responses. No, it's back.
Guys, can you hear me?
Yeah,
Yes.
we asked
Yeah.
you at smaller.
I said that, like, if I had to guess what might come next, it might be, and not anytime soon, like not in the next 6 months, but maybe further down the line, maybe we'll add something to the production system that works over smaller primes for more efficiency. And after that, further down the line, I think definitely things like ECStark will appear. But if I have to guess, I'd say, let's say in a year and a half, small fields, and then maybe in 2.5 years, ECFFT.
Awesome. Everyone is invited to implement it before us.
Yeah,
I think
sure.
quite soon after our first paper on EC50, there was an external implementation in Rust that someone made for comparison. It tested, I think, multiplication, which EC50 is not best suited for. But other than that, I think it was pretty neat.
I saw there was a question about expander-based Starks or PCPs. So I should say that I'm guessing it's referring to like gap amplification techniques of Dinu or these other things, or maybe it's referring. There's even newer works on like constant rate locally testable codes. So both of these things are right now completely impractical from a concrete point of view. Not anytime soon. The expander-based codes, they're like very, very. I'm not even talking about the encoding time, just the constants on like PCP proof length and things like that. They're like very, very, very bad.
Ellie, a bit off topic, but you mentioned that for Cairo you use a 252-bit field. Did I hear that correctly? Why?
Yeah.
Right.
Why?
Don't get me started.
We wanted
yeah.
we wanted to prove ECDSA, which needs a curve of this size for security, and we didn't want to do extension fields ECDSA because it wasn't compatible with other implementations in the market.
Okay, I see.
I think, well, I don't know if it was intentional, but there are also some benefits where when you implement the Ethereum contracts that have to verify the StarkNet and StarkX proofs, you can gain something by not using the full 256 bits because you can do some additions without caring about the overflow before you have to do modulo operations. So that's nice.
Right.
Yeah, but I lament that, you know, I mean, it's like if I had a time machine, like, I would go back in time, maybe I would change that. But I'm hopeful that at some point we'll add smaller fields because it's a shame not to have the extra efficiency and just, I don't know, it's nicer to use smaller fields. Okay, guys, I need to jump off.
Okay, if we don't have any more questions, just want to say thanks very much to Ellie, Dan and David. Thanks very much for joining us, fielding the questions.
Thank you, everyone.
Thanks, and please implement it, someone.
Thank you, everyone.
Thank you.
Okay.
Bye.
Bye.